In our previous lesson, we discussed finding the limits of sequences. And in this lesson, I want to start off by finding the limits of summations. And early on in the year, or I should say earlier in the year, we actually discussed finding the sum of an infinite geometric series. And in that process, we were actually using the concept of a limit without even knowing it. If you recall the sum of an infinite geometric series, and remember what an infinite geometric series is, it's a series that doesn't end, right? So we're constantly adding terms, but every subsequent term is determined by multiplying by a common ratio. So this next one, I would say something like A1 times R2, and so on and so forth. And you can actually rewrite this in sigma notation as such. So our upper index is infinity, and our lower index, we're actually going to use I here. I know we were used to using N before, but we're going to use N in a second. So I'm going to just say I for lower index. And we would say something like A sub 1 times R to the I minus 1. And if you recall, what we did is we would just kind of summarize this by writing this as such, right? If you recall, this was the formula to find the sum of an infinite geometric series, where, and this only applied when the absolute value of your common ratio was less than 1, right? It's a fractional value between 0 and 1. And using the limit notation, now that we have the limit notation under our belt, we can actually describe that same sum as the following. We can say it's the limit as n approaches infinity of, now we're going to use n as our upper index, I is equal to 1, and a sub 1 times r to the I minus 1, so effectively what we just had in the previous step, and we can just rewrite this as such. And we're not doing anything different here. We're just incorporating limit notation now into this idea of an infinite geometric series. Well, we now have a list of summation formulas and properties that we can use to evaluate finite and infinite summations. And this one is actually in your textbook, and I'm just going to go ahead and copy it and paste it here. And let me go ahead and actually just make this a little bit easier for us to see, because I think all this above, just go ahead and just leave that there. This is in your textbook at the beginning of 11.5. And so what I'll often be doing is I'm going to have you guys refer back to these. In calculus, we don't use these all the time, but since we're starting to develop a fundamental understanding for how this stuff works, it's a good idea to have this under our belts. So take a moment, review these. I'm not going to go over every single one, but just know that these are summation formulas we can use to evaluate finite and infinite summations. Okay, so let's do one model problem. I'm going to model one problem for you guys and then give you guys an opportunity to try another one on your own. Okay, so let's go ahead and try a couple of these actually. We'll do a few. So first off, we've got this in sigma notation. And ask yourself, which of the properties would we want to use here? Well, if we go back to our list, probably just want to go ahead and use this one, right? The one with I squared. So using that, we can say the following. We could say that this is equal to, just evaluating, let me just kind of zoom in on this, n times n plus 1 times 2n plus 1. I'm just rewriting the formula all over 6. Well, what is n in this case? N is going to be 30, so 30 times 31 times 2 times 30 plus 1, which is just 61, all this over 6. And I'll spare you the math, that just comes out to 9,455. So here's the sum of this finite series here. This is a finite series. So we found the sum using the summation formula. All right, let's try another one. Now let's take a look at this one. Now at first glance, none of the formulas apply here because we've got k cubed minus 3k squared. But there's a pretty easy workaround. All we need to do is just rewrite this. So let's write this as the sum from from 1 to 10 of k cubed minus, and I'm going to just go ahead and write that 3 on the outside here, algebraically just comes out to the same thing. It's equal to 1, 10, and k squared. Now, if you go back to our formula list, you'll see that in this case, we can now use the cubic, which was summation number 4, along with the quadratic, which was rule number 3. So now that we know that we're going to use those two rules, let's go back to our problem now. And we're going to write this as the following. This would be 10 squared times 10 plus 1, so 11 squared, all over 4. And all of this here, we're going to write this 3 on the outside. And let's just do some work here. So we're going to go 10 times 11 times 2 times 10 plus 1. So that's going to be 21, all over 6. And from there, I'm going to just save you the work of writing it out. Again, you can always check this on your own, and you should be. And this comes out to 1,870 as our final answer. Okay, and that didn't want to make my box for me, but let's try it again. All right, there we go. Second time's a charm. All right. So these were very basic examples of just showing how we could find the sum of these particular series using those formulas. All right, let's try a lengthier problem now. So let's try this problem where we're given this particular limit, and before we find the limit, we're actually gonna rewrite the sum here as a rational function, s of n. We're gonna write it as the sum of some n value. So given a certain number of terms, we can find the sum. And we're gonna use our formulas here. So our idea is to use the formulas and properties that we jotted down from the beginning. And we're going to find a way to rewrite this. We're going to want to rewrite this here so that we can apply those formulas. That's our goal. And then we'll write this as a function of n. So let's try this. So our first thing, now that we know what our first part is, so our first part is to see which of those properties might make sense there. And the fact that we have that n squared in the denominator is going to kind of debilitate us a little bit. So I'm just going to factor it out, which we're allowed to do, right? We can just write this as 1 over n squared. That's a weird looking n. And the sum from I is equal to 1, and our upper index is n. Now this is 4i plus 3. Okay, and as I go along, you know what? I'll just write out our steps. We're going to factor out our constant 1 over n squared. Because 1 over n squared, that's just a constant. That's not affected at all by what's going on with I. All right. Now in our next step, we saw that 1 over n squared on the outside, but just like we did in our previous problem, let's separate these two terms using the summation properties. So I'm going to write this as, and I'm going to factor out 4 from the first term that I've separated out. So I is equal to 1, and here's n. So all I have so far is just this term. That's all I've done. Okay. Now we've got this summation, I is equal to 1, n of 3. Okay. And all I'm doing here is separate using properties. Okay. All right, we're going to continue on now. So now that we have that, we're going to apply the formulas. So 1 over n squared, and this would give me 4 times n plus 1 all over 2 plus, and then this next summation, since it's just a constant, it's pretty easy. It's just going to be 3 times whatever n is. Again, we're just applying summation. All right. And then from here, we just need to simplify, right? From here, it's just algebra. So 1 over n squared, well, that 2 goes into 4 twice. And so we just have 2n squared plus 2n plus 3n. And again, all we're doing here is we're just simplifying. And to clean that up even further, we can just write that 1 over n squared times the quantity of 2n squared plus 5n. Okay? And you know what? might as well just kind of keep going at this. This can be cleaned up even further as 2n squared plus 5n over n squared, which is just 2 plus 5 over n. And all this now leads us to our summation. This is now our rational function. So all this here, okay, you know what? That's equal to our S of n. So what we've just done is we've used those formulas to rewrite this limit of the summation as a rational function. All right? Okay, so from here, now for part B, this is the kind of mind-numbing part, but the one that hopefully you'll find fairly easy. We're just going to evaluate the sum now. Now that we've written this summation as a function, let's just evaluate the sum for a certain given number of n's. So what is it when n is equal to 10, 100, 1,000, or 10,000, right? So we're just going to quickly do these. So I'll just show the work for a few, and then after that, I'll just give you the answers. So we got 2 times 10 plus 5 all over 10, right? That's just going to be 2.5. And you know what? I realize it might have been a little bit confusing that I left it in this form, because I could have also said this. Sorry, I should have specified this. That you might have wanted to leave it as this. It doesn't really matter, right? But now hopefully you can see where I was getting that math. So S times 100 is equal to 2 times 100 plus 5, all of that over 100. And again, you can just use either one. They're the same thing. 2.05. And now you can kind of see where this is going. 2.005, and then the sum of the first 10,000 terms is now going to be 2.0005. Okay, so that's all we're doing there. All right, and part C is what I think might be the easiest part, is we're just going to find the limit of S of n now as n approaches infinity. So we're going to find the limit as n approaches infinity of our S of n, which is, again, the limit as n approaches infinity of 2n plus 5, all of this over n. Well, what is that? In this case, it probably makes a whole lot more sense just to divide everything by n. So now we've got 2 plus 5 over n. So as n approaches infinity, this is going to approach 0. So all of this is just equal to 2. Okay, so think about what's happening here, what we're saying here. We're saying, given this original limit here, the limit of the summation, we can come up with an equivalent function, S of n, using the summation properties. Now that we've written it as that function S of n, we can easily evaluate the sums. Since we've already used the formulas, we can quickly evaluate the sums for any given number of n. So the sum of the first 10 terms, the sum of the first 1,000 terms, the sum of the first, I should have underlined the last one, 1,000 terms, the sum of the first 10,000 terms. Well, what would the sum of an infinite number of terms look like? It would be 2. And we can intuitively see that by what's going on with the sums that we found in part B. We can see that they are approaching the value of 2. It goes from 2.5 down to 2.0005. So the limit of this function is 2 as n approaches infinity. So hopefully that makes sense, and I will go ahead and work out the next problem on the back, and you can just go ahead and check your answers on my completed note sheet. And next, we'll then use this idea of the limit of a summation